All right, so now you need to forget about everything we discussed regarding the localized electron model and orbital hybridization, because we're going to discuss a sort of different theory of covalent bonding, which is called molecular orbital theory, or MO theory for short. This theory relies on a mathematical superposition of atomic orbitals to calculate molecular orbitals. And that's done through linear combination. So this acronym stands for linear combination of atomic orbitals to form molecular orbitals. Basically, that's just a fancy way of saying that you're adding together the atomic orbitals. And when you add together atomic orbitals through linear combination, you have to add them together, but you also have to subtract one from the other. And doing both of those things gives you both a bonding and an anti-bonding molecular orbital. So the guiding principle here is that the number of atomic orbitals that you add together are going to be equal to the number of molecular orbitals that you get from the linear combination. So all of that might seem very technical and abstruse, but I'm going to clarify it now with a couple of examples. And I want to start with the simplest molecule we can, the H2 molecule. H2 is, of course, just two hydrogen atoms bonded to each other. And we know that hydrogen atoms just have the 1s orbital. So each of these is going to have a 1s orbital associated with it. And I'm going to label them 1sa and 1sb for hydrogens A and B. So now let's do a linear combination. We're going to add those orbitals to each other. We're going to add 1sa to 1sb. And the rule for adding orbitals together through linear combination is that whenever you add them together, you also have to subtract one from the other. So I'm going to create a molecular orbital by adding them together, and I'm going to create a second molecular orbital by subtracting one from the other. Now, we know that 1s orbitals are spherical. So I'm just going to draw a little 1s orbital here, and I'm going to indicate its phase with a plus sign. So that plus sign is not a charge, it's just indicating the phase of the wave function. Now, what we're doing is we're going to add two waves together that have the same phase. And when we do that, the matching phases produce what we call constructive interference. This is just like adding two waves together that are in phase. So we are adding them together constructively to make the wave even taller. That's called constructive interference. So what happens when we add those two together is we're just going to get one big molecular orbital with the same phase. Now, let's go over to the side where I'm subtracting one from the other. So if I'm subtracting 1s orbitals that have the same phase, let me improve the look of that one just a wee little bit. That's the same as saying, let's see, if I reverse the signs here, I can say that I am subtracting a wave with opposite phase from the initial wave. Okay, so these two things are equivalent. I'm just switching the signs. So if I do that, what happens? Well, imagine that these are approaching each other. There's going to be destructive interference because I'm adding together opposite phases. So when opposite phases combine, they combine to produce destructive interference. Combine to produce destructive interference. So they're going to cancel each other out as they come together in an overlap. They're going to at least partially cancel each other out because their waves are going to interact destructively. So what that's going to do is it's going to kind of shrink those lobes a little bit, and it's going to produce what we call a node in between the two lobes. Okay, so again, what I'm talking about here is that we have this guy being added to this guy, and when they approach each other, they're going to partially cancel each other out, and they're going to produce this node in between them. A node is a region of 0 electron density that is going to be between the two nuclei, the hydrogen nuclei in this case. Now, that's very different from what we saw over here. Here we had enhanced electron density between the nuclei because of that constructive interference. So we see these very different situations through the two linear combinations that we just discussed. When we have the enhanced electron density along the bonding axis like this, we call that a sigma bonding molecular orbital. So this is going to be my bonding molecular orbital. This one over here with the node is what I call an anti-bonding molecular orbital. And you can kind of see why, right? We have the region of 0 electron density between the nuclei. That is not a bonding type of situation. So since the electron density here in the bonding MO is along the bonding axis, not above and below it, but along it, we call it a sigma MO. So what we have here is a sigma bonding MO. The anti-bonding MO is a sigma star. So this little star that I put next to the sigma, that star means anti-bonding. Okay, so this is my sigma star anti-bonding molecular orbital. And this is my sigma bonding molecular orbital for the hydrogen atom here, the hydrogen molecule rather.